Good day, class. We are now on Unit 3 of our Biochemistry course, and our topic is on water. In this PowerPoint video, we will talk about the importance of buffers in biological systems. 60% of the average human is made of water, and most of these are found in our blood. As allied health students, you should know that our blood is 83% water. So that makes sense why we first discussed the properties of waters, looking into its fitness as the medium for transport substances in our body. We also discussed pH in Unit 3.2 because it is important that pH of blood is about 7.4, which is slightly basic, or else we get sick. Hence, in this topic, we will look into how pH is maintained in our body.
But first we look at why it is important to maintain pH in our blood. From the book, we saw some effects when the pH of blood becomes acidic and when the pH of blood becomes basic. You will learn this in clinical chemistry. There are two organs that regulates pH. We have lungs, that is responsible for the respiratory control and affects PCO2 or acid in our body. And we also have kidneys. Kidneys are the ones responsible for the metabolic control and handles bicarbonate. So given that our blood is around pH 7.4, it tells us that it also dissociates, that there is a dissociation of water going on. But how is our blood able to maintain its pH? So the main reason how we maintain pH of blood at 7.4 is the presence of weak acids and weak bases. And we know that these weak ones do not completely dissociate and instead establishes equilibrium. Do you remember Le Chatelier's principle from your inorganic chemistry or analytical chemistry? Le Chatelier's principle states that if a reaction mixture at equilibrium is disturbed by a change, the system will shift its equilibrium composition in a way that tends to counteract the change in an attempt to re-establish equilibrium. So it seems like nothing happened because it can easily adjust its state. Again, in your book, an example of the weak acid given is your carbonic acid. And this carbonic acid can be found in your blood. Carbonic acid can dissociate in water to give hydrogen ions and bicarbonate. And this bicarbonate here produced is a conjugate base. But this bicarbonate here can react also with your hydrogen to form the carbonic acid. You see here, we have the reverse arrow as well. Now, not all weak acids are the same. Some are stronger than others, and this can be measured using the acidity constant Ka. But we can modify this to pKa using the same formula, just like our pH, negative log Ka. And just like our pH, the lower the pKa, the lower the pH. So unlike when you use Ka, the lower the Ka, the higher the pH. For any acid HA, the relationship between pKa, the existing concentrations, the conjugate base, and the acid at equilibrium, and the pH is given by the relationship known as your Henderson-Hasselbalch equation. So this equation is important because we use this to prepare buffers. Before proceeding to the calculations, we first go to this question. What is a buffer? So many of us know that buffer is a solution that can resist changes in pH. Again, As MLS students, what is clear for you should be that a buffer is a solution that contains equal amounts of weak acid and its conjugate base, or a weak base and its conjugate acid. Now, our blood needs to have a pH of 7.4, but we have an acceptable range of 7.35 to 7.45, and it has 3 buffer systems to help keep it maintained. So we have the carbonate buffer system, proteins can also act as buffers, and the phosphate buffer systems. We've already seen how the carbonate buffer system works in the previous slides, and this is actually the major extracellular buffering system. This is important in respiration, and on the other hand, our phosphate buffer system here is the major intracellular buffer system and is good in dissociating when a base is added to the system. To prepare a buffer solution, we must prepare an acid conjugate base pair. So we go back to this Henderson-Hasselbalch equation, and this A negative here is actually either a conjugate base, and this one is your acid. So for the example that we have a while ago, our carbonic acid, this is our carbonic acid, and this here, the conjugate base, is your hydrogen bicarbonate. So what we want to do to make it a buffer is that pKa must be equal to pH. So how will we do that? So if you do this to your calculator, you put log is equal to 1, that will give you 0. And this one will be equal to pKa. So therefore, we want the base and the acid ratio here almost equal to 1. So let's look at some questions in your activity for this unit. So what is the pH of 0.9 EQ of base when it is added to a solution of the fully protonated acetic acid? So we start with the Henderson-Hasselbalch equation. We have pH is equal to pKa plus logarithm of base over acid. So given is that 0.9 EQ of base is added to a solution. So we need to take note that 0.9 EQ base will convert 0.9 EQ of acid. Therefore, we have remaining 1 minus 0.9 of the converted acid. We have remaining 0.1 EQ of the remaining acid in the solution. And then we will need the value of pKa. So for that, you will need this table here, or any table that you found on the net. So you have here the pKa for acetic acid. We have 4.8. We just plug in those values and we will see what value will we get. So pKa is 4.8 plus log of base would be given is 0.9, and we've computed the acid, which is 0.1. We have remaining 0.1 because 0.9 is converted by the base above. So that gives us 4.8 plus 0.95, and this gives us a pH of 5.75. So you need to try this on your calculators. So let's have another example where you can relate more, but this is not included in your activities for this unit. So for example, you are tasked to make a buffer. You need to calculate the ratio of the concentrations of acetate and acetic acid required in a buffer system with pH of 5.30. Of course, we will again start with the Henderson-Hasselbalch equation. What we are looking for here is the concentration, not the concentration, it's the ratio of the concentrations of acetate and acetic acid. So we will transpose this on the other side so we can easily compute for these ones. Okay, so we're down with this one. pH is given. We have the value 5.30. How about pKa? pKa of acetic acid, we got that in the table from the previous slide. It's 4.8. Therefore, 5.30 minus 4.8 is equal to 0.5. And we get the antilog of this one to cancel the logarithmic term here. So antilog will give us the answer 3.16. Therefore, the ratio of the concentrations needs to be 3.16.
So for your activity 3.3, you will just differentiate the carbonate buffer and phosphate buffer systems in terms of pH and pKa and give functions of each. So what have we learned from this unit? First, we talk about what is buffer. Second, what is the importance of buffer in our body? And third is how is buffer calculated?